Hello and welcome to this video on electromagnetism and current carrying wire. In this video we're going to recap some work on magnetism and we're going to look at what happens to compass needles when they are next to a wire that is carrying a current. A magnetic field is an area around a magnet where the magnetic force can affect other magnets and magnetic materials. The field gets weaker the further away you are from the magnet and is the strongest at the poles of the magnet. And you can see this from the field lines. The closer together they are, the stronger the field. So the poles have field lines close together. This is a strong field. The sides of the magnet have a weaker field strength. The field lines, as you can see, are further apart. The field lines have direction. They always go from north to south, and this should be shown by arrows on your diagrams. The needle in a compass is actually a small magnet. It usually points to geographical north as it aligns itself with the magnetic field of the Earth. If another magnet is placed close to the compass will change direction and it will align with the magnetic field of the closer magnet. This is important to note when using compasses to do experiments with magnets, and indeed you can use a plotting compass to find the magnetic field lines of a bar magnet. The needle in a compass is a small magnet. It usually points north as it aligns itself with the magnetic field of the Earth. If another magnet is placed close to the compass will change direction and align with the magnetic field of the magnet. Here we have a vertical wire attached to a power supply. The vertical wire is put through a cardboard shelf, and on that cardboard shelf are placed some small plotting compasses. With the power supply switched off, the compasses all point north, which is exactly what you would expect. But when you switch the power supply on, the compasses change direction. They move so that they are arranged in a circular pattern around the current carrying wire. When the current is switched off, the compasses go back to pointing north. And if you change the direction of the current, the compass needles change direction. All of this is evidence that there is a magnetic field around a current carrying wire, and that this field can be switched on and off with the current. As we have seen, a wire with a current going through it has a magnetic field, and that field is only there when the current is flowing. But what's the shape of the field? If we replace the compasses with iron filings, we can see the field a little clearer. The iron filings line up with the magnetic field lines, and the shape of the magnetic field around the current carrying wire is concentric circles. Where the iron filings line up with the field lines, we can see a pattern of concentric circles. This is the shape of the magnetic field around a current carrying wire. As with bar magnets, the strength of the field around a current carrying wire changes with the distance. The further away you are from the bar magnet, the weaker the field. This also happens with a current carrying wire. The further away, the weaker the field. However, with a current carrying wire, you can increase the field strength by increasing the current. The field lines around a current carrying wire have direction in the same way that the field lines around a bar magnet have direction. To find the direction of the field lines around a current carrying wire, you need to use the right-hand grip rule. The right-hand grip rule shows the direction of the magnetic field in relation to the current. The thumb points in the direction of the current, positive to negative, and the way that the fingers curl around shows the direction of the field. Here they show the field has an anti-clockwise direction. If the current is going in the opposite direction, so downwards in this case, then you would point your thumb down and your fingers would curl in the opposite direction, and they would show that the field lines have a clockwise direction. And that's the end of this first video on electromagnetism. Thank you so much for listening.